Is it clear? The voice is okay?
Yes.
Clear?
Yes, sir.
So today we'll start some group theory application in combinatorics. So this is also a very broad subject. So let's see how much we can do, because we have roughly a month in hand now. There are many other topics. So maybe we will not be able to do a lot, but some basics we will be able to do. So some people told me that they already have group theory from other course, right? BSc, the group theory is already covered to some extent. Is there any MSc student in today's class, for example, who has not done group theory, even starting group theory? Is there anybody from MSc in today's audience? So what I'll do, I'll quickly brush up some basics of groups, very basic. So it is, you have done much more in the math class, but since I do not know what is the background of all the people, I'll just quickly brush up groups. And our goal will be to see some combinatorial application using group theory. So can somebody tell me what is the last theorem that you have studied in group theory? Let's say what is going on currently. Understand. Any word?
Sir, today we looked at the correspondence theorem, the one which talks about there being a bijection between the like if we have a quotient group and we have the natural homomorphism to the quotient group, the one which talks about the bijection between the subgroups of the quotient group and the groups of the original group containing the kernel of the homomorphism. That's it.
Okay. Yeah. Okay. Have you done this group action, orbit stabilizer, these things already?
And not in class, sir. No, I think sir said he was going to start that next week.
So we need, I mean, see these things. The course is designed in an independent way. That's the problem. Okay, so let's not worry too much and let's quickly revise some basics. If there is anybody in the audience who has not seen formally group theory, then it will be useful. So we all know what groups are. Closure property. Just quickly revise. There is identity element. So my objective is not to teach you group theory, but just to connect it with combinatorics. Associativity. Inverse. Yeah, so these are the 4 properties, and groups can be either commutative, group operation commutes, or they could be non-commutative. Okay, so let's quickly have some examples. For example, z plus set of integers under usual addition. If you take real number and delete the 0 and take the multiplication, that also forms a group. These are like commutative group. You can take this group SL2R. It's like set of 2 cross 2 matrices of determinant 1 over reals. These are non-commutative group. Yeah. So we have this notion of isomorphism. This is introduced already, the notion of isomorphism.
Yes, sir.
Okay, so let's quickly define. So G is isomorphic to H if and only if there is a bijection phi from G to H such that phi of G1, G2 is equal to phi of G1 times. So here the operation in H, here the operation in G. Okay, so also we have the subgroups. Subgroups, as the name suggests, it's a subset that is a group under the group operation. For example, SL2R, usually for the subgroup we use this notation, is a subgroup of GL2R. This is like group of all invertible matrices. Okay. Right. So for a subgroup H, we have this notion of coset. And there are some basic properties of cosets. So let H be a subgroup and AB belongs to G. Then either the coset either the coset is same or they do not intersect, right? So just to refresh, so this is very simple property. If they intersect, there would be an element C inside it. So C, you can write it like AH1, which can be also written as BH2. Right? So H will be BH2 H1 inverse. So that will be in the coset BH. Imply AH is a subset of BH. Similarly, BH has a symmetric argument. So cosets is disjoint, right? And for doing combinatorics, the most important picture that we keep in mind is that there is a group G and there is a subgroup H, and these are its cosets. This picture is very useful, right? And of course, like size of all cosets are same. So the number of cosets is G by H. That number is sometimes denoted by G colon H. This is also called index. Index of this is just a Lagrange theorem, right? So this goes like our just basic introduction of groups. There is nothing new in it. The one class of groups that we will be very interested in combinatorics is the permutation groups. This is studied in details in your math course already, permutation groups. This is very important. Is it studied in the course already?
Sir, we defined it and like some basic things.
Okay. So let's quickly define. So take set of 1 to n. What is a permutation group? You collect all the permutations from n to n. These are like permutations. So pictorially, a permutation can be nicely denoted by to n. There should be some number, right, where it maps. If you don't understand something, just stop. I'm just assuming that you know it, so I'm going a bit fast. Okay. So this is a set. The cardinal key of the set is all possible permutations, and it is a group under composition operation. So what do I mean by that? If you take two permutation, pi1 and pi2, you can compose. If you can define a new permutation, right? Pi1 compose pi2. What is the meaning of pi1 pi2 compose pi2? The meaning is simple. Pi1 act on pi2 x. So pi2 will send x somewhere, and pi1 will act on that. So under this composition operation, that it's an easy exercise. Forms it. This group is called symmetric group. Yeah. And in combinatorics, we will be always mostly we will be interested in permutation groups. So permutation groups are the subgroups of symmetric. Have you studied that theorem in the class? Like any group is some sense behaves like a permutation group. Kelly's theorem, have you studied?
Yes, sir.
That theorem is very nice, but it is not very computationally efficient because it maybe you have to embed in a really huge size symmetry group. Okay, so
Sir?
Yeah.
So you have written permutation groups are the subgroups of symmetry group. Aren't they the same?
Meaning?
Like, aren't symmetric groups just permutation groups?
Yeah, but any subgroup of symmetry, so permutation group is a class of groups. Any subgroup of symmetric group also you call it as a permutation group.
Oh, okay. Yeah.
For example, these have different kind of groups that could be solvable, that could be abelian, but they are all permutation. They are subgroup of a symmetry. Right? They could be nilpotent.
Yes.
Okay, so another basic definition, like sometime we need that automorphism. We don't need it immediately. I'll give you later a few pictorial examples. We don't need that much. So automorphism of a graph, it's a bijection from the vertex set to the vertex set. It's a bijection such that phi maps edges to edges. Such that if UV is an edge, P can only phi U phi U. Any questions so far? Particularly people who have not seen groups, I just quickly defined some basic concepts of group. If there is anybody who has not seen group, let me know whether you find it difficult to follow anything particular. Anybody from MSc joined? I know that there are several people who are crediting for MSc, but I don't know whether anybody is in the class. Okay.
Sir. Sorry.
So
Sir.
yeah, your voice is getting disconnected. I cannot hear you.
Sir, I just
don't know
wanted
the
to.
Problem from my side or your side. I cannot hear your voice.
Can you hear now, sir?
I'm not able to. Sorry, I mean, I don't know that. It is giving a message that my internet connection is unstable, so I'm not able to hear you.
Oh, sir, maybe I'll just.
Yeah, can you repeat?
Yeah, sir, this is just recording, sir. I think the recording is not started.
Oh, sorry.
Recording in progress.
We don't lose much. There is nothing. I mean, I will provide the note. This is like textbook material. So let's look at some other definition. So, okay, so when you study the permutation group, you always have a set in mind, right? Here, for example, here the set is like 1 to n. And you should think of like the group is acting on the set. That means action simply means that where it, if you take a group element, let's say G, where it is mapping 1, where it is mapping 2, where it is mapping 3, these are the actions, right? So in studying permutation group, we always have a action in mind. So there is a set and the group is acting on it. Okay. So let S be a set. More concretely, you can think of like S is 1 to n, and G is a permutation group. Acting. So notationally, we always write G acting on S in this sense. Some people prefer, okay, I'll use this notation. This notation means G acting on S. And now fix any I in S, right? You can define stabilizer of I.
So what do you mean by acting on S?
So that's what I said. Like whenever I'm talking about permutation group, you always have a set in mind. Like if it is a subgroup of 1 to n, that 1 to n is your set. And the group is sending some, if you take a group element G, what is the action? It is sending 1 to somewhere, 2 to somewhere, like that.
Oh, okay.
But I mean, group action need not to be always defined only for the permutation group. There are a variety of other cases, but we are not going into that. Like in algebra, you will see the group action in more general sense. And there is nothing particular about just permutation group. It can be defined in a more general setting also. But since we will be doing only combinatorics, we are concentrating on the properties of permutation. Oh, I forgot, before I go here, I forgot one thing. So I defined the automorphism of a graph. Here is a simple exercise. Prove that the set of all automorphisms, very simple exercise, automorphisms form a group. That group is known as auth of G. So auth for automorphism. Okay, so for any I, fix any I, you can define the stabilizer of the I. Stabilizer of I is defined like Gi. That is those elements in the group, it is the same group that is acting on S, such that when you take the element I and apply G, this is the notation like G acting on I. You apply the operation or the group element G on I, it does not move it, it fixes it. The definition is clear?
Yes, sir.
So this is again a very simple exercise, that GI is a subgroup of G because just because of the composition. If G1 fixes, if I take I G1 compose G2, which means like I G2 and then you are making G1, which is clear, right? Because both are fixing I. So if you take their composition also, they will fix I. Okay, so for example, if you let's take a 6 symmetric group on 6 element. Let's take I equal to 1. Then what is G1? G1 is a set of permutations that has mapped 1 to 1. It has fixed 1 to 1. It does other things, it does in its own. 2 to 6. So all possible permutations are possible with the element 2 to 6. Only one it fixes, right? So what is that group G1?
S5.
Yes, so G1 is isomorphic to S5 because all possible combination of 5 elements are allowed. Only one is fixed. Now, if you take example 2,
Sir,
yeah,
sir, in the definition, S is not actually any arbitrary set, right? I mean, S contains only such elements on which G can act upon. I mean, G is a particular
yeah.
permutation group.
Yeah, it's like meaningfully defined. You cannot take G to be.
Okay,
Yeah.
sir.
Whenever you're talking about permutation group, you have that universe in mind, right? It is not some arbitrary. I mean, this is not acting over, for example, reals. You cannot. There is no meaning of that kind of.
Okay.
It's, whatever naturally comes here, action is restricted to that. Okay, so if you take a CN cycle on n vertices, n is let's say at least 3. So, now look at that some vertex I. What is GI? So this is a cycle on n vertices, right? And 1, 2, maybe some 3. And I want to see the subgroup that fixes I, right? And there are I minus 1 here, there are I plus 1 here. So what that subgroup can do? What is that subgroup that fixes I?
Identity element.
Hmm?
Identity.
Yes,
Identity.
identity, yeah, but is it only identity? Any group has identity, right? You can fix everything that is identity. But is there any other element in the group of GI That's the stabilizer of I.
Reflection about I. Okay, that needs cryptographic defense.
Actually, unfortunately, my internet connection is very weak today. I'm not able to hear the voice of most of you properly. It's very unstable, the internet.
No, I was telling reflection about I, but that would require the order of the group to be 2n.
So I don't know, that someone already answered because I am not able to hear. See, I'm getting a message that my internet connection is unstable, so I'm not able to hear you. There is some problem with my connection today, but probably someone was telling. So if you swap this, these two things, right? There could be a permutation that can swap or exchange between I minus 1 and I plus 1, right? And then if you exchange, the other things will be fixed. So I'm sorry, I'm not able to communicate today because there is internet is very poor. GI is 2 elements, either identity or I minus 1 goes to, sorry. So this is basically isomorphic to S2. It's written in the chat. So, okay. And as I wrote, that GI is a subgroup. That's easy to see. So another important definition that comes into combinatorics is orbit. Orbit of an element. So pick any element I from the set that you are working on. You can define the orbit, I power g, that's the symbol. The meaning of orbit is very simple. Orbit for the point I is a set of points where I will be moved by the group action. That means I of g will be I when g acts and moves I to somewhere else. And g is running over the group, whatever acting on S. Let's say G is a group acting on S, and given an element I, you can define the orbit. So intuitively speaking, orbit is where I is moved by the group action. A very basic lemma in combinatorics is that if G is a finite, all groups are finite for me, so I don't write anything finite especially. G is a permutation group. Group acting on a set S, and I belong to S. Then G is the cardinality of the orbit times the stabilizer subgroup of I. Cardinality of G. Is the statement is clear of the lemma? It's a very important lemma used in combinatorics. Internet is very poor, not able to communicate. So hopefully things are clear. So how shall we prove the lemma? It is very simple. So G is the full group, and I know that GI is a subgroup, right? Now let's look at the cosets. So that could be G1 GI, G2 GI, and so on. Right? And GI fixes I. So if you take H to be a coset element, let's say coset from G, first coset, and apply I power H on it, what will be the case? It will be G1 and some group element. So this is like I will be acted by H, and then it will be moved by G1. But H fixes I because H is coming, sorry, it should be H prime. So H prime fixes I because H prime belongs to G. So, right? So this I power H will be moved to wherever I power G1 goes. That means every coset element will move I to a some element, right? And an easy observation is that, okay, some people also write this I power G action as same as writing. Some book will use it just simply they call G of I, same meaning. Now, if you take two coset, if you look at I of G1, or rather I use a different notation. If G1I equal to G2I, if they send I to the same place, then what does it mean? That will mean that G2 inverse G1 will move I to I. That means Z2 inverse G1 will be in the stabilizer of I, implying that G1 is in the coset generated by G2 of the stabilizer. That means the distinct coset representative. So this G1, this guy G1, G2. So this G1, G2, G3, they are called coset representative. That means if you take different coset representative, identity is also included for the first coset, then they will move I to a different points. Right? And that's precisely the orbits. So the size of the orbits equal to number of cosets. Size orbit so this imply that you take orbit and multiply the coordinate of the group. This is the full group. This has a special name in group theory. This is called orbit stabilizer lemma. Yeah, I think running a longer class will be difficult. I'm not able to communicate. I'll do some more, but maybe the class will end early because my internet is not allowing me to talk freely. It is very unstable. So another definition we need to before we do the combinatorics, if G is a group acting on the set S and small g is the element of G, you can define the set if G. If G is those I in the set S such that G fixes I. So it's like kind of complement of orbits. Orbits means where I is moved by different element. And here, like given an element, you look at what are the things that G has fixed. That's called FG. This is a fixed group. This is a fixed points. Fixed points of G. So let's just, since I'm not able to communicate, let's just pause. Let me pause for a few moments and digest these definitions. So we have defined three things so far. The stabilizer. So there is a group action on a set S, and given an element, we have defined the concept of stabilizer. Stabilizer is simply, it's a subgroup, the group element that fixes the given element I. Okay. And then there is a second concept of orbit, where an element I is moved by the group action. That's the orbit. And the third concept is given an element, you can define its fixed point. That set is denoted as FG. And there is this nice relation of orbit stabilizer lemma shows that the cardinality of the orbit times cardinality of the stabilizer is the full group. Okay, so now we are ready to state and prove one very important theorem that will be heavily used in combinatorics, where group theory is used. So that lemma is called Burnside lemma. So let G be acting on S. Then the number of orbits of S under G is 1 over G. G belongs to G. So this is a very fundamental statement proved by Burnside. It gives you a closed formula to compute the number of orbits of the set S when G is active. If you know the size of all these FC sets, just sum them and divide by the cardinality of this statement about finite groups. Let me just pause for a moment in this statement. Can you at least hear me properly? I'm not able to exchange communication.
Yes, sir.
So I hope the statement of Burnside lemma is clear. Let's try to prove this lemma. So let m be the number of orbits. This G. So we need to prove that m times G is equal to summation of G F G. This is what we have to prove. Actually, the proof is very elementary. The statement is very powerful. And the proof is very elementary. So look at the right hand side. So it's a two-line combinatorial argument. What is the right hand side saying? It's adding over the cardinality of this sets Fg. So recall for your convenience that Fg is a set of I in S such that G fixes I. That's the fixed points of the commutation G. So the right hand side is exactly same as number of, if you think for a moment, so number of Gi tuples such that I is in Fg. If you open up and add, every Fg account one unit for one such tuple G, comma I, right? So definitely the right hand side is accounting for all such tuple Gi such that I belong to Fg. So on the other end, I need to count it from two sides. If you stare at this equation, counting from two sides, this is also same as summation of Gi I belong to S. Because what is the summation of Gi I belong to S? This is also counting the tuples Gi such that G fixes I. I'm just looking the same thing from two sides, one from the F side and one from the stabilizer side. Right? So that implies if G is equal to, now you know that by orbit stabilizer lemma that this is same as G by I prime I times, so by orbit stabilizer lemma. But now just divide both sides by 1 over G. But so now this inverse term I have to estimate, right? But this is very easy. How do you estimate it? Let G be an orbit of size K. Now I is running over the set S. So how many times this 1 over K contribution will be there? For every element I in the set S, you will have a contribution of 1 over I power G if for exactly K times, right? Is it clear? So the size of the orbit is K. So the 1 over I power G will be 1 over K. And every element that exists in that orbit, when you look at their partial sum, they will all contribute 1 over K in that whole sum, because they are always in the same orbit. They are coming from the same orbit. That means every orbit computes. If you compute the sum in the right hand side, every orbit gives you exactly 1. So just writing it in a different
We
way.
just get the number of orbits, right?
Right. This is like the number of orbits equal to, and that's what Burnside lemma claims. So this number of orbits is exactly this quantity. Let me go back. So there are two things in group theory that helps very much in combinatorics. One is the Burnside lemma, another is Paulius counting theorem. And this Paulius counting theorem, I don't know whether we'll have time, because then the group theory section will take a lot of time. So maybe we have to restrict ourselves to Burnside lemma. But this is the statement.
Sir, could you repeat the name of the other theorem you mentioned?
Paulius counting theorem.
Okay, sir. Thank you, sir.
That's more advanced, but it can be taught, but then it will take more time. Okay, so this was the first plan of device of group theory. So let me know whether anything is unclear so far. So far we haven't done any combinatorics. We have just devised some basics of group theory. Particularly to people who have not seen group theory. I think many algebra book will give you sufficient exposure to this element, this permutation groups and related thing. One book that's a simple book, but I find it useful, is by John Fraley. This book by Fraley has a lot of material on this kind of group actions and concept from permutation. I don't know how much Atin has it. Probably Atin also will have a lot, because Atin has a chapter on group action, I guess. Any standard book will have it. Harstein, I am not sure though. Harstein has enough of these things. So any question on these things? Okay, so we'll see one application. There are plenty of applications of Burnside theorem. Some of them are quite difficult, and some of them are not so difficult. So we'll see one application. So the question is, so while I'm doing it, I want to illustrate you some situation where this kind of abstract group theoretic statement will help in counting some concrete object. So let me just state the problem. So find the number of distinguishable ways in this equilateral triangle. Can be colored using 4 colors. So this is the question. Find the number of distinguishable ways of coloring the edges of an equilateral triangle using 4 colors. Some color can be used any number of times. So now what I mean by distinguishable? Can anybody guess what could be the right notion of distinguishability in this kind of problem? Sometimes some book will not even say what they mean by distinguishable. But what could be the most logical way you can think of?
The two colorings will be distinguishable if we can't get one by reflection or rotation from another. That
Right.
is,
So yeah. So since I'm talking about some graph theoretic thing, so one coloring will be distinguishable from the other if it can be obtained by the automorphism of the graph. Let's fix that notion of, since we're talking about graph, let's fix that notion of distinguishability. There is a nice name for it. So indistinguishable if one can be moved to the other. That means you label the vertices of the graph by an automorphism of the graph. Here it is it's a triangle, and you see the same color basically. Okay, so let's see what it means. So our graph is K3, right? So let's find the automorphism group of K3. What are the automorphism groups of K3? And what is the size of the automorphism group? One automorphism, of course, will be identity. So if you have 1, 2, 3, it will be mapped to 1, 2, 3. That's the identity. What are the other automorphism of K3?
I think the group will be S3 and size is 6.
Exactly. So it will be S3, and one can also, if someone is looking at it for the first time, I'll just do it explicitly. It is S3, yeah. So basically, it will have this identity element and the 3 cycles: 1 move to 2, 2 move to 3, 3 move to 1, or other way. Or it will have 2 cycles and a fixed point. Right? So because that will give you some intuition why this is used in the combinatorial. So let's write the automorphism group more explicitly. So this is identity, and let's look at the fixed point: 1, 1, and then 2 goes to 3, 3 goes to 2, then 2, 2, 1 goes to 3, 3 goes to 1. Then
Sir, actually, as the graph is complete, so any permutation will be an automorphism.
Yeah. So I'm just, because I want to do it exactly so that you can develop some intuition how at the moment this counting of different colors looks like a totally different problem than group theory, right? So since it's the first example, I'm doing it, it's little more elaborate so that you see, often it will be difficult to reduce this kind of completely a counting problem to a problem in group theory, and this reduction is the toughest part. So that we develop some intuition, I am just doing it from the first principle, like brutally, just listing out everything, so that we develop some intuition what's going on. You are right. So one may skip all what I am doing also. So this is the 3 cycle, and then 1 is like 1 goes to 3, 3 goes to 2. And since you have not seen permutation group that extensive way, I'm just doing it. So these are the, as someone said, is isomorphic to S6. So this is S6. Sorry, S3. So these are 6 7. Okay, so now look at the Burnside lemma statement. So to compute the number of orbits, so the G value we got. So this is the group that is acting on a set. So what is a set? The set S is the set of all possible coloring. Right? So what is that number? Any edge can be colored in 4 ways. So the cardinality of S is 4 power cube. It's like 64. So this is the set, and your group of this automorphism of K3 acting on this set, and it leaves a few things indistinguishable. So what are the indistinguishable elements you think by this abstract definition, that group of automorphism is acting on a set of coloring when one color can be moved to other color by the automorphism? Or in other way, what is the nice thing about all the indistinguishable colors? If you think for a moment, they are basically an orbit, right? Because what is the meaning of an orbit? One element is moved to the other by the action of a group, which is the automorphism of K3. And that's our notion, that they are different if one cannot be moved to the other by an automorphism. So it basically says that the number of distinguishable coloring is basically number of orbits. Is that intuition is clear?
Yes, sir.
This is the difficulty of this line of investigation, that you have to frame this abstract or the totally different looking question into a group theoretic framework. So,
Sir, could you explain it once again?
yeah, so we know this Burnside lemma at our hand, right? That's a tool we have. And this lemma gives a way to compute the number of orbits under this group action. Now this group we identified, that is the automorphism group of K3. That's isomorphic to S3. And the set is the set of all colorings, right?
Yes, sir.
And when do you say two colors are indistinguishable? The notion of indistinguishable is that if they are equivalent up to an automorphism. That means you can move from one to others by an automorphism.
Okay, sir.
Right? That means all the colors that are sitting inside an orbit, they are indistinguishable. So they should contribute 1. because you don't overcount them. So basically, this question asks you to count number of orbits.
Okay,
under
okay, sir. Yes, sir. Now I get it.
Yeah. So it's enough. Enough to count orbits. Is active on this. Right? And we know that to count that, it is enough to compute the fixed point for each permutations. That's the Burnside level. There is a nice formula that for every permutation, if we can compute the number of fixed point, I just add it and divide it by the cardinality of the group acting, I will get what I want. Right? So now our job is very concrete. So let's look at, so what is F of identity? Means if you have this triangle, irrespective of whatever color you put on these edges,
That's 1, right, sir?
no.
So you put the mod around it. So
Mod means the cardinality.
yeah, that's what the cardinality is 1, right?
No, it is like, what is the definition of FG? FG is the number of element in the set S which is fixed by the permutation G, right? Now the permutation G is identity here for you. But identity will fix any coloring, right?
Okay, right. So 6.
Whatever color you use in these edges, so this is 64, basically 4 power 3. The whole set is fixed by this coloring, right?
Yeah, I get it. Sorry, I got confused.
No,
Yeah, I get it now.
That's fine. Yeah. Now let us look at what happens when you have these 3 cycles. So basically you take these 3 cycles, these 2, and try to understand which coloring is fixed by these 3 cycles. 1 goes to 2, 2 goes to 3, 3 goes to 1. Can somebody guess what will happen? You can compute it. Basically, you take the triangle and color and try to understand if it is a 3 cycle, which coloring it will keep fixed.
So only colorings are all 3 are the same.
Exactly. So the 3 cycles will fix the colorings which uses same color on 3 edges. Okay. So that means let's give it a name. So this is the identity. So this is let me call it sigma 1, sigma 2. These are elements. Sigma 3, sigma 4, sigma 5. So I want to compute. That means f of sigma 1 equal to f of sigma 2, and only 4 ways. As I said, all things should be colored in the same way. So this is 4. And now let's look at what is the cardinality of f sigma 3 and f sigma 4. So they are like 2 cycles. Obviously, by symmetry, their number should be same, but what are that number?
Sir.
That's right. How do you get that?
2 edges have the same color and the other edges another color. Okay, 4 into 4.
So right. So the two cycle, that two edge will have the same coloring, otherwise you will have a conflict. And the other edge can be colored in any ways, like any of the four ways. So this is equal to 16, basically. If you just do it offline, if you are not convinced. So this is a total sum then out of K3, and divided by the group cardinality is 6. And if you add all of them, this is 120 by 6, which is 20. So these are the number of distinguishable coloring that you obtain by this group action. So it will be nice if you elaborate this example. Because if you have seen the first time at home, you can elaborate on this example and try to understand it completely if you have any problem in understanding. Because sometimes the problems of this Burnside lemma can be very tricky. Particularly, how do you attach a group theoretic setting with a counting problem may not be always easy. This was not so difficult problem, but sometimes it could be difficult. I cannot teach lot here because that will involve this dihedral group and all these things. I don't know whether people know these things. So I will stick to some very few simple examples. So this, since the internet connection is not very stable, I will not extend today's class. Also, it's just 5 minutes. So I will maybe do it in the next class. So we'll try to do some more examples, but not using heavy group theory. Whatever simple group that you understand. Yeah, that's the plan.
Recording stopped.
So yeah. If you have any question, you can ask. So did you get the marks of the assignment, the first assignment grading?
No, sir, I don't think it was complete.
No, did you get the feedback from the assignment, first assignment?
Some problems were marked and we were given feedbacks.
So you don't know your feedback.
Not there, is it? The total marks?
No, I don't think so.
Okay.
Then what feedback you received from TS for the first assignment?
No, the document was annotated in the sense like containing, I mean, the problem to problem, some of the problems were checked out of the 15, I think 7 or something number of problems were checked, and out of 5, the marks were given, and if they cut marks, they gave feedback, annotating in the document.
Okay. So annotation not there means you have got full marks. That's the way they are going.
Yes. Even in case of full marks, they wrote it that you got 5 at the end of the document, the last page, something like that.
Yeah, because of the online, these things are difficult to coordinate, and they are trying to give you the feedback for the mid-sem by around, I guess, 15th April. And the second assignment is due when?
14th, I guess.
14th. Okay. So by the end of April, you will get the feedback for the second assignment also, and mid-sem by 15th April.
Also, just wanted to know, have you all done a course on number theory before? Like, is that running currently?
No, I don't think there's any course on number theory running for the BSc first year. I think so. The question that she asked, are you doing any course on number theory also along other things in this semester?
No, sir. No, ma'am.
Okay. Yeah, thanks.
because there will be some module in number theory also in
Hmm.
discrete,
Yeah, in case you already know stuff like just graph theory, I just wanted to.
where we'll cover some cryptographic stuff also along with the basic numbers. Okay then.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.